All right, welcome to our snow day video. Let's pick up from where we finished in class on Friday. So again, we're going to be rewriting Newton's laws in spherical coordinates, just like we did with cylindrical and plane polar coordinates. But this time, as we talked about in class, we're not going to go through the argument as this thing rotates, this thing changes, and etc. in the same way. We're going to do it a slightly different way to make it a little bit easier. So the way we're going to do that, as we talked about in class, is we're simply going to take our unit vectors, which in this case they are r hat direction, and then we're going to project that onto the x, y, and z planes. So that way we can rewrite all of our unit vectors and spherical coordinates into Cartesian coordinates. So that way, when we take the time rate of change of those, our coordinates are just going to be time independent, which means the derivatives are going to be equal to zero. So the way we're going to do that is we're going to start off with, say, this picture here. So I'm going to take my coordinates here. All right, my x, y, and z. So here's my r vector. So there's my r hat direction. First, I'm going to project that down into my xy plane. So that's going to give me the sine portion. So I'm going to get an r hat sine of theta. And then I'm going to project that then onto the x-axis and the y-axis. So for example, we're going to take our r hat sine of theta in the xy plane, dotted then with the x hat direction. According to our angle, that's going to be the cosine portion. So then we're going to get what? A sine of theta cosine of phi. Doing the same thing then with the y portion. So that's going to give me then a sine of theta sine of phi. Now for the x portion, or the z portion, I should say, so here we don't have to bring it down into the xy plane. We're simply going to project this guy onto this axis. So this is just going to be the cosine portion. So from here, we're going to get a r hat dotted with a z hat, and then is equal to simply cosine of theta. Okay, where again, theta is our azimuthal angle, or the angle rotated from the positive z-axis. So this means that I can rewrite r hat then as equal to sine of theta cosine of phi in the x hat direction, plus then sine of theta sine of phi in the y hat direction, plus then cosine of theta in the z hat direction. Now, we're just going to do the same thing then with both the y or the theta direction as well as the phi direction. I'm going to skip all those steps and just write that down for you. So we should find then is that our theta direction is going to be equal to then cosine of theta, cosine of phi in the x hat direction, plus cosine of theta sine of phi in the y hat direction, minus then sine of phi in the z hat direction. And then finally, our phi direction will then just be equal to minus sine of phi in the x hat direction, plus then cosine of phi in the y hat direction. Fantastic. So now we have all those things. So basically all we're going to do now is take time rates of change of those. Again, I'm only going to do this for the r direction, so we can kind of see what we're doing here. But again, let's go back. So I want the time rate of change of the r hat direction. So going back to my slide previously, so here I have a product of two functions. I'm going to take the derivative of the first times the second. So that's going to give me a what? Theta dot. Let's go back. So I'm going to get a cosine of theta. Where am I? There I am. Cosine of phi. That's the first in the x hat direction, plus a derivative of the second. So derivative of a cosine is a negative sign. So then I'm going to get a minus phi dot, and then we're going to get a sine of theta, sine of phi in the x hat direction. And again, I would take the derivative of x hat, but that's just going to give me a zero. So I'm going to skip that term. So then we're going to get a plus a derivative of sine, which is going to give me a theta dot. And then we're going to get a cosine of theta, sine of phi in the y hat direction, plus phi dot times then sine of theta, cosine then of phi in the y hat direction. And then finally, we're going to get a minus sine of phi dot in the z hat direction. So good. So let's group all of our terms together. So in the x hat direction, we're going to get a theta dot, cosine of theta, cosine of phi minus phi dot, sine of theta, sine of phi. Mhm. Let's see. Do I want to do it this way? Actually, I don't want to do it this way. Let's just combine like terms together. How about that? That sounds smarter. So basically, all I'm going to do in this case, I'm going to put all my theta terms together, or my theta dot terms together, and then I'm going to put all my phi dot terms together. So let's do that. So let's do it that way. So let's do a theta dot, and I'm going to get a cosine of theta, cosine of phi in the x hat direction. And then I'm going to get a plus cosine of theta sine of phi in the y hat direction. Good. And then we're going to get a plus phi dot. And then I'm going to get a sine of theta cosine of phi minus sine of theta sine of phi minus sine of phi, all in the z hat direction. Mhm. So cool. So basically, if I go back now, and I look at these terms here, what I can find then is all the terms which are multiplied then by theta dots are simply the same thing as my theta direction. Right? And then all my terms which are multiplied by the phi dots is the same thing as my phi direction. Mhm. So we could see that from here. So finally, what I'm going to get in this case then is this works out then to be a phi dot times then sine of theta in the phi direction plus, then we're going to get a theta dot in the theta hat direction. Right? Now, if we do the same thing for the other two directions, what I get in this case then is the time rate of change of theta direction is then going to be equal to minus theta dots in the r hat direction plus then phi dots in the cosine of phi. And then finally, d phi hat dt is then going to be the same thing then as what? Minus phi dot sine of theta in the r hat direction minus then phi dots cosine of theta in the theta hat direction. So putting all these things together, what we then get is that our velocity, which is the time rate of change of the position, is going to be equal to r dot in the r hat direction plus r times the derivative of the r hat direction, which then turns out to be using what we just did above. So r dot in the r hat direction plus r times theta dot in the theta hat direction plus r phi dot sine of theta in the phi direction. Now my acceleration then would then be equal to the first derivative of the velocity, which is then going to be equal to r double dot from the first term, r hat, plus r dot, r hat dot from the first term as well, plus r dot, theta hat, plus r theta double dot, theta hat, plus r theta dot, theta hat dot, plus r dot phi dot sine of theta in the phi hat direction plus r phi double dot sine of theta in the phi hat direction minus r theta dot phi hat, or sorry, phi dot cosine of theta. Cosine. Oh, sorry, there should be a positive. There we go. Cosine theta in the phi hat direction. And then finally, r phi dot sine of theta in the phi hat dot direction. Okay, so finally, using what we did above, so putting in all of our unit vector derivatives and then combining terms together, we're finally going to get the following. So this is going to give me an r double dot minus r phi dot squared sine squared of theta minus r theta dot squared in the r hat direction plus r theta double dot plus 2r dot theta dot minus r phi dot squared sine theta cosine of theta in the theta hat direction plus r phi double dot sine of theta plus 2r dot phi dot sine theta plus 2r theta dot phi dot cosine of theta in the phi hat direction. Okay. So these is the acceleration. So again, the r's, especially the derivatives of those, are just the accelerations in the radial direction as well as the velocity in the radial direction. The second term in pretty much every one of these, well, at least all the ones that go as r something dot squared, these are all centripetal terms. So these are all centripetal accelerations. So i.e. this one, and looks like that's it. So those are centripetal terms. Good. And these are centripetal around particular different axes. So whether it is the azimuthal or the uh, polar angles, and that's about it. So great. And then again, to get the forces acting on each one of these guys, we just simply multiply the acceleration times the mass to then get Newton's second law. And then to get the momentum, we're just simply going to take the velocity and multiply it by the mass. But I'm not going to bother rewriting each one of those because it would just take forever. So let's not do that. So good. So that's the velocity and acceleration in spherical coordinates. Most of the time, we're not going to work too much with spherical coordinates. I'm not going to worry too much about doing an example with this, but we'll do some when we actually need them. So good. So now that we have done Newton's laws in curvilinear coordinates, now we can go back to the fact that, again, mass can be time dependent, which basically means that, again, as we mentioned, things can actually cannibalize themselves to propel themselves. So all that means then is, again, Newton's second law said that the sum time rate of change of the momentum is then equal to the force, right? Now, if the mass is not equal to a constant, all that's going to do then is give us an extra term, which is going to look like the time rate of change of the mass times the velocity plus then the mass times the acceleration. All right, so we pick up this extra term here, which has to do with the rate at which the object is cannibalizing itself. So the rate of cannibalization, I'll write it. Cannibalization. Don't know if that's a word, but I'm going to call it that anyways. So, and as we mentioned in class, this happens for things like cars, our bodies, rockets, etc. So these all actually cannibalize themselves to propel themselves, right? So let's do an actual example of this. So let's look at rockets. Let's see how this guy actually works. So rockets. So good. So first of all, let's talk about our viewpoint. So our viewpoint is going to be from somebody who's standing on the ground watching this actually occur. Okay. So let's say at some t, so this is going to be our initial time, the rocket, say, is here. So here's my rocket. Great. And let's say it has some instantaneous velocity at this point with a velocity of v, and this has an instantaneous mass of m. Okay. So that means then that what? Initially, according to this person, the initial momentum will simply be equal to the mass times the velocity. Great. So let's go a little bit further. So now let's say at some later time, and this is going to be some time of t plus dt, so some small interval of time later, we're going to have some exhaust, which is given out. So this is my exhaust. So my exhaust then is going to have some differential amount of mass. So it's taking away a small amount of mass from this object. Now, for now, I'm just going to call this positive when I write out everything, but we're going to note that in the case of a rocket, anyways, that this mass here, this differential mass, will be negative. At least, yeah, as far as the rocket is concerned, right? Because the rocket's mass is going to decrease. So the rocket's mass now is going to be the same thing then as m plus dm, where again, m is going to be, or at least dm is going to be negative. It's taking away. Now, this is in the case of the rocket. Now, if I had something like a water droplet, as I mentioned in class, falling down through a cloud, its mass is actually going to get bigger. So in this case, I'm going to get m plus dm, where dm in this case will be positive. Right? So it's ultimately going to depend on the scenario, but here I'm just going to write it in general as a positive, and then we'll have to know by context of if it's actually positive or negative. Now, at the same time, the velocity would have increased. So my final velocity will be the initial velocity plus some sort of increase in velocity. Now, simultaneously, the gas here, or the exhaust, will be coming off with some velocity. Let's call that V exhaust. So that means that according to the guy on the ground, we have two different objects then. So we're going to have the momentum of the rocket. So the momentum of the rocket then will be its mass, which is m plus dm, times then its times its velocity, which will be v plus dv. Okay. Now, here, of course, I'm calling this as my positive x-axis, both since both this term and this term are both positive. Now, simultaneously, the mass here, or my differential mass, I should probably call that. So PDM, there we go, is going to be moving in the negative direction. So I'm going to pick up a minus of its mass times its velocity. Now, its velocity will be the relative velocity. Now, in this case, since the rocket overall is moving to the right with a velocity of v, and the excuse me, the exhaust is coming in the opposite direction as with its own velocity in its own reference frame. So this V exhaust here is in its own reference frame. Then in this case, since it's moving in the opposite direction, the total velocity this guy's going to have, according to the guy on the ground, will be the relative velocity, which will be its velocity minus then the expulsion velocity. So this means then that the total final momentum will be equal then to the momentum of the rocket plus then the momentum of the differential mass, which is going to be the same thing then as the mass, plus then dm times v plus dv minus then dm. There we go. Times v minus v expulsion. So cool. So let's write that out a little bit more. So my momentum at t plus dt is going to be, so let's multiply everything out. So I'm going to get an mv plus a v dm plus an m dv plus a dm dv, and I'll come back to that in a second, minus then v dm minus, or a plus in this case, since I have a minus, v expulsion times dm. Now, let's look at this term here. So this term here is an infinitesimal times an infinitesimal. So this is an infinitesimal, let me just call that d delta squared. Now, this term here, compared to all these other terms, which only have a single delta, in this case, this is going to be basically zero. So this term compared to the size of the other terms will basically just be zero. So cool. So that one term is gone. Okay. Cool. Let's keep going from there. So finally, my final momentum, or so my change of momentum, let's write it that way. So my differential change of momentum is going to be my momentum at t plus dt minus then my momentum at t, right? So this is my final momentum minus my initial momentum. So I'll plug that in. So I'm going to get an mv plus, in this case, also notice that this term here is the same as this term, so that's going to cancel. So I'm going to get an mv plus mdv plus v expulsion times dm minus mv. So of course the two mv terms are the same, so we're going to get rid of those. So my change of momentum then is going to be simply equal to mdv plus v expulsion dm. Okay. So going back to where we started, this is basically this term. The only difference here is that this is not the instantaneous velocity the way it's written here, but this is the velocity of the expulsion times then what? basically ma, okay? Without the dt's, of course, because I have to put the dt on the final to make it the acceleration. So finally, what we also know is that the time rate of change in momentum, based on what we did earlier in the semester, is equal to the total external force times dt in this case. And so finally, we can write mdv plus v expulsion dm is then equal to simply the external force dt, or finally, m dv dt plus v expulsion dm dt is equal to the external force. Beautiful. So basically, all this means then is we can determine exactly the velocity as a function of time if we know the external forces acting on the system. So let's do some examples of this and see how this basically works. So the first example I'm going to do is when the external force is equal to 0. So basically, all we're saying here is here's my rocket, and let's attach that to, say, some train tracks, and then let's just send it off in its merry own direction this way. So this is my V. Okay. So in this case, the only forces which are acting on it are going to be my normal force acting on it in this direction, as well as my gravitational force acting on it this way. So that way my net force acting on it is simply equal to 0. So cool. So let's talk about this real quick. So first of all, going back to what we just did, we know then that we're going to have a what? V expulsion dm dt plus my mass times my dv dt is then equal to 0. Okay. So basically all this means then is that what? V expulsion m dot must then be equal to minus m v dot. Or typically, we're going to write this as mv dot is equal to minus v expulsion times m dot, where the second term here, the term on the right-hand side, is what we usually call the thrust. So this is our thrust. So this term here, m dot, this is the rate at which the rocket is burning or ejecting fuel. So what? So basically, our what we have to do now is simply what? Calculate and determine what this thing is doing. Okay, so basically we want to find the velocity as a function of time and see what this thing is actually doing. So we want to find out what is our velocity as a function of time, or what is the velocity as a function of mass. So let's talk about this. So first of all, let's talk about some expectations. Right? So let's talk about some expectations. So what is this thing going to do? So first of all, what we know is that there's going to be some sort of limit to our mass of the rocket, right? So the rocket is not going to expel all of its mass. So what we have to say then is that the rocket is going to have some sort of mass of the rocket, right? So let's say here that what? We're going to have some mass. So this is mr, which is the mass of the rocket. And then this is going to be our final amount of mass. So this is going to equal our final mass. And then let's say here we have some m0, which is going to be equal to our total mass, at least our total initial mass, which of course is going to be equal then to the mass of the rocket plus the mass of the fuel. Right? So, what's going to happen? So, what we know is that what this thing's feeling some sort of acceleration causing it to speed up, but eventually that mass is going to go from the initial amount of mass down to the mass of the rocket. Now, when it goes to the mass of the rocket, is it going to be able to keep accelerating? Well, the answer, of course, is no, because once it expels all of its mass of the fuel, it then is going to go from whatever initial velocity it has to some sort of final velocity. So in this case, we know it's going to go from some initial velocity to some sort of final velocity, where that final velocity will then be equal to some sort of constant when the mass goes down to the mass of the rockets, right? So basically, this thing is going to reach some sort of terminal velocity. So this thing is going to reach some sort of terminal velocity. Mhm. Wonderful. Now, what we also know is that at some point, this is going to have a mass, or at least the terminal velocity, I should say, is going to have to somehow be a ratio of the initial mass to my final mass. And from the structure of it, we can actually see it has to be some sort of natural log. So, but we'll see that in just a second. So these are our expectations. So we know that this thing is going to increase its velocity, but it's only going to increase so far that it's going to reach some sort of a maximum velocity once all of the fuel has been changed over. So yeah, if I knew how to speak. So if all of its changed, or if all of its mass has been expelled until it has the final rocket mass. Okay, so let's work on this. So let's go back to our differential equation then. So what do we know? We know we have m times dv dt is then equal to minus v exhaust times dm dt. So first off, we have dt's on both sides, so let's cancel those two. So great. So we're going to get rid of our time components in this case. And then from here, we're then going to have what? M dv is then equal to minus v expulsion dm. So basically, all we want to do now is what? Do separation of variables. So we're going to bring everything that's an m on one side and everything that's a v on the other side, and then just solve our differential equation. So in this case, we have nothing that is a v, because v expulsion here we're assuming is just a constant. So I'm going to get a dv integrated from my initial velocity to my final velocity is then going to be minus v expulsion, since that's a constant, integral of dm over m from my initial mass to my final mass. Right? And I'm just going to leave this as a generic final mass instead of the mass of the rockets, which we know will be the absolute final mass. So good. Integral left-hand side, we have a dv, which integrated becomes just a v. So I'm going to get a v minus v initial is then equal to minus v expulsion. Integral of 1 over m dm is the same thing as natural log. So I'm getting a natural log of the ratio of m final divided by m rocket. Okay. So cool. So finally, we get our final velocity will be equal to our initial velocity plus, and I'm going to change the order of those two, v expulsion, natural log of the initial velocity divided by the final velocity. Okay. So in this case, I'm just swapping and changing the order of the inside to make it positive. So good. So what does this thing say? So this thing says that what? The velocity is growing as the natural log of the initial mass to the final mass, right? And we know that the initial mass will be bigger than the final mass since it's cannibalizing itself. So meaning that we're going to have a number here which is bigger than 1, right? So basically at m is equal to m0, my initial velocity or my final velocity is just equal to my initial velocity because natural log of 1, of course, is just 0. So in this case, it's growing, right? The velocity is growing. So finally, what we know is then at m goes to mr, my final velocity will then be equal to the initial velocity plus v expulsion times then the natural log of simply the initial velocity to the velocity of the rocket. And this is when it reaches terminal velocity. So this is going to be my terminal velocity. So my terminal velocity again is when all of the fuel is expelled, so that we have simply then just a ratio of the initial velocity to the mass or to the final I say initial velocity, sorry, the initial mass to the final mass, which is simply a constant term. So this is going to reach some sort of constant velocity. Right? Now let's think about this. So is this going to be a very large number? So for example, let's say that the ratio of the initial mass to the mass of the rocket is 10. Okay. So basically, the amount of the rocket is only 10% of the total mass of the rocket and the fuel. So basically, most of it is fuel, right? So let's look at this. So natural log of 10 is actually only 2.3, which means that the change in velocity is actually just equal to 2.3 times the expulsion velocity, which is actually really small, right? So if your expulsion velocity of your rocket is, I don't know, let's say 100 miles per hour, probably more than that. But anyways, let's say 100 miles an hour. That means your final velocity is only going to be 230 miles per hour. Mhm. So basically, it's this reason why we have multiple stage rockets, right? So basically, you start off with a multiple stage rocket where you have the bottom portion where this thing is basically all fuel. Mhm. Great. So this is fuel. And then you have basically the rocket on top of that, right? So basically what happens is initially you fire this guy, so it reaches some sort of final velocity, right? So this is going to be the velocity of stage one, at which point in time it's going to jettison this portion so that now the only thing we're going to have then is going to be this rocket, which is now firing, where now it's going to have some velocity of stage two. So basically, by jettisoning this portion here, you're massively then dropping the mass of the rocket, right? So you're going to massively decrease the size of this because this guy's going to have some sort of a massive, let's call that massive C for the container. So it's going to drop that off, and then it's going to fire again to now increase its velocity even more. Mhm. So basically, during the first stage, right? So the final velocity of the first stage then is going to be the initial velocity plus then the expulsion times then the natural log of then whatever the original total mass is. So I'm going to write that as then Vm total times then the mass to start then the second stage. Mhm. Or now, after that, my final velocity for the second stage then is going to be equal to what? The velocity at the first stage. Actually, this should be the mass of the first stage. Sorry about that. There we go. Plus then the expulsion velocity. This final portion of my iPad never wants to work. It's a natural log. There we go. Then my mass after the jettison. So this is then there we go. Mass after divided by the mass of the stage two portion. So basically, substituting this now into here, what we finally get then is that the final velocity becomes equal to the initial velocity, plus then the expulsion, times then natural log of, well, we have a natural log, right? Plus a natural log. Remember, the natural log of a plus a natural log is the same thing as the product of the inside. So this is then going to be equal to the total mass of the jettison, I think I called it, divided then by the two masses, right? And then if I had another stage, I would just end up with another ratio on the inside. So basically, by doing, no, I don't want to do that yet. So basically, by jettisoning these and doing them in multiple stages, we can get greater and greater and greater and greater amounts of velocity. So that way we can get further and further away from the surface of the Earth in this case. Okay. So good. So this is our first example. So let's look at our second example. So our second example is going to be then with gravity. So it's going to do with gravity. Now, in this case, I'm going to use only the gravity near the surface of the Earth. So my gravitational force in this case is going to be our usual m times g. So we're not going to do the gravity away from the surface of the Earth, which is a lot more complicated. So in this case, we're just going to use this guy. So good. So in this case, all we know then is that our external force in this case. I wrote it in the opposite direction. There we go. Force external will then be equal to, at least magnitude-wise, equal to simply mg, which is the force due to gravity. Now, for this, let's say our rocket is moving upward. So in this case, my rocket's moving upward. We know the acceleration due to gravity is downward. So this says then that what? The mass times dv dt plus v expulsion times then dm dt will then be equal to a minus mg because that'll be in the opposite direction in which it is that we're going. Mhm. So now we have to solve this differential equation. So let's make first an assumption. So let's say our assumption in this case is number one, that m dot is equal to a constant. So let's pretend that over the entirety of the trip vertically in this case, that the rocket is giving off or expelling its velocity or it's expelling, sorry, its mass at a constant rate. So this is going to be equal then to some constant, let's call that minus alpha. Just to make our lives a little bit easier, that way we have less terms we basically have to solve for. So this term here is just going to be simply a constant. So now we only have basically one thing which is changing with time. Okay, so now we have a differential equation which only depends on time and uh, velocity, excuse me, which we can rewrite in terms of the mass, but we'll do that in just a minute. So again, let's talk about some sort of expectations. So what are my expectations in this case? So my expectations are similar. So we're going to have some sort of maximum velocity, right? So in this case, what we know is that when the mass, or in this case, my initial mass goes down to the mass of the rocket just before, my final velocity then is going to be going to, again, some sort of terminal velocity. Well, maybe not terminal velocity, but let's call that Vmax. It's going to be some sort of maximum velocity. So what's happening then is it's going to be accelerating upward at some acceleration until the mass in this case switches over, right? And it's going to switch over at this stage to now the acceleration due to gravity, right? So basically what's going to happen is it's going to feel some sort of acceleration until this acceleration is going to go zero, where my rocket in this case then is going to have its maximum amount of velocity. Once that happens, it will now basically go under free fall. So ultimately, it's going to start at some height. It's going to go to some height. Let's call that burnout height. At which point in time, the acceleration that it has will go to zero. It'll switch over then to the acceleration due to gravity, at least the increasing acceleration. And then it's going to go under free fall until it reaches some other max height in this case. So this is going to be then some extra portion, but ultimately this thing's going to reach some max height from the ground. So basically our expectations are it's going to increase its velocity, reach some sort of maximum velocity. When it reaches its maximum velocity, then it's going to switch over to the force only due to gravity, and then it's going to increase its height under free fall, and then eventually it's going to stop, turn around, and then come all the way back down. So these should be our expectations. So cool. So let's solve our differential equation. So again, now we know we have what? So we have m dv dt minus m alpha, or sorry, not m alpha. So this is v expulsion alpha, there we go, is then equal to minus mg. Now, let's solve this guy. Now for the velocity, let's do it in stages. So I get a dv dt is then equal to v expulsion over m alpha minus g. And then finally, let's multiply both sides by dt, use our separation of variables. So finally, I'm going to get a dv then is equal to, let me write it this way, minus g plus v expulsion over m alpha dt. So cool. So now all we have to do now is integrate our differential equation here. So let's go ahead and do that. So let's multiply everything through. So first, before I do that, let me kind of rearrange some stuff. So first things first, let me go ahead and pull out an alpha. So I'm going to get a minus g over alpha plus v expulsion over m, all then times alpha dt. Now, Why am I doing this? So I'm doing this because, so the way it's written here is this is going to give me what? The velocity as a function of time. However, notice that there's this term here, right, which is the mass term. If my pen will actually write, there we go. But my mass term is, of course, a function of time. So the way it's written here is I can't actually solve this differential equation until I know how the mass depends on time. Now, I can find that, and we will find that in just a minute. But what I'm going to do now is I'm going to rewrite it in this form because what I want to do is just like in a previous case, I want to find the velocity as actually a function of the mass, right? And what we know is from our previous slide here, we know that the dm dt is the same thing as minus alpha, which means dm then is equal to minus alpha dt, which means that alpha dt is the same thing as minus dm. So basically, I'm going to replace this term here with minus dm to write this now as a differential equation with respect to mass. Okay? So let's do that. So finally, what I'm going to get then is dv is then equal to, so the minus sign is going to cancel on the first term. So I'm going to get a g over alpha, good, minus now v expulsion over m. And then all of this then is going to be multiplied by dm. So this tells me then that integrating both sides, so I'm going to get a v minus v initial from the left-hand side, then is going to be equal to g over alpha integral from my initial mass to my final mass of then simply dm plus v expulsion integral dm over m from my final mass to my initial mass. So I'm just pulling in that negative sign and switching the order of those two. So let's do that. So my left-hand side is, again, v minus v0. My right-hand side is going to become g over m, or sorry, g over alpha, m minus m initial, plus v expulsion times the natural log of my initial velocity divided by my final, or sorry, my initial mass divided by my final mass. Keep saying that. So good. So basically, all this means then is what? So again, we can see it reaches some sort of maximum velocity, right? Because in this case, when m goes to, let's do it this way. Yeah, m goes to m rockets, both this term and this term are again going to be simply equal to a constant. So they're going to become just a maximum velocity. Now, after that, it's hard to see that it actually switches over to the acceleration due to gravity. Now, to do that and show that that's actually true, let's start off with our dm is equal to or minus alpha dt. Right, let's go back to this. So let's integrate both sides of this. So I'm going to integrate from my initial mass to my final mass. This side I'm going to integrate from my initial time to my final time. We're going to say my initial time is simply 0. So in this case, we're going to get an m minus m initial is then equal to minus alpha t. So this term here is actually the same as this, which means my final velocity is going to be equal to my initial velocity minus g over alpha t plus v expulsion, natural log of the initial mass to the final mass. So finally, I can write this whole entire thing in terms of simply the acceleration, right, due to gravity. So again, all this means then is when this term here becomes a constant, this term here does not become constant because t can actually keep increasing, right? Which means that what? This thing does switch over to the acceleration due to gravity since this term cancels, or at least this term becomes a constant, right? So this term is eventually going to become a constant. And then this term with this term become the usual kinematic equations for constant acceleration. So kinematic equations for constant acceleration, where a is equal to simply g in this case. So cool. So let's use this. Let's do an example using this stuff. So my example says that what? Let the mass of the fuel at burnout be the final mass, or the mass of the rocket. So let's call it mass of the rocket. So this is when it burns out. And it wants us to calculate the altitude and the speed of the rocket at burnout. Okay. So let's call, first of all, capital T equal to the burnout time. So this is when we've exhausted all of our fuel. So then my mass becomes simply the mass of the rocket. So cool. So in this case, let's find our velocity at this time. So first of all, let's use the fact that we know T then is equal to, from above, the initial mass minus the mass of the rocket, all divided then by alpha. So this is my burnout time. So my velocity then is going to become equal to whatever my initial velocity was, minus then GT burnout, plus V expulsion, times then the ratio of the initial mass to the mass of the rocket. Or using this guy here, this is going to be equal to my initial velocity minus then g of the initial mass minus then the mass of the rocket, all divided by alpha, plus then v expulsion, natural log of the ratio of the two masses. Great. So this is my velocity. So this is my velocity at burnout. So let's call that v burnout. So now what I want is height burnout. So first of all, what do we know? We know that v is then dy dt. Using our separation of variables, this means then that the height, so y, is then going to be equal then to the integral of the velocity integrated over time from my initial time to my final time, or in this case, I'm saying y initial is simply equal to 0. So cool. So let's plug all this stuff in. So first of all, what we want is the height of burnout. So let's call that h burnout. Then is going to be equal to the integral from 0 to time of burnout of the velocity integrated over time. So this then is going to be equal then to my initial velocity times my burnout time. Okay. And then we're going to get a minus g integral t dt from 0 to burnout. And then we're going to get a plus the expulsion divided by alpha integral from my initial mass to the mass of the rocket, natural log of m over m initial dm. Okay. So basically, all I've done is I switched the order of the natural log term. Okay. And then I'm using again the fact that what? dt is then minus dm over alpha. So I'm replacing that last term then with simply the dm since I already have it in terms of the mass. Now, of course, I could use the time and use the time of burnout, but that's a little more complicated, so I'm not going to bother doing that. Okay. So let's put everything together. So this becomes V0t. Now for the rest of this, I'm just going to say V0 was 0, just make my life a little bit easier. Minus then 1/2 GT burnout squared. Okay, we'll replace that in just a second. And then what? So here, let's define a new variable. So I'm going to call this plus, and then we're going to get a V expulsion alpha M0 times what? The integral of the natural log of x dx, evaluated then from 1 to the ratio of mr over m0. Okay, so what did I do? So I took the ratio of m over m0 and defining that as some x. So that means then that dx is the same thing then as what? dm divided by m0. Okay. So basically, I'm using that into here. Okay. Something tells me that M should not be there, but that's okay. So in this case, from my initial, of course, M0 or M0 is just going to be 1, and then that's my relationship between the last part. And then notice that the integral of what? Natural log of x dx is just the same thing as x natural log of x minus then x. So good. So let's plug that in. So finally, my height of burnout is going to be equal to minus 1/2 GT squared plus V expulsion over alpha times then, from here, I'm going to get a ratio. So I'm going to get then x, natural log of x minus x. There we go. Evaluated from 1 to mr over m0. Okay. So let's put all that in. And then finally, at the end of the day, we're going to get a h burnout is then minus 1/2 G, now let's put in what T is. So that's going to give me an M0 minus M rocket squared over alpha squared plus V expulsion over alpha times M final natural log of, actually it's going to be M rocket, sorry, natural log of M rocket over the initial mass. So here I'm just pulling in M0, so that's canceling out that M0 there, plus M0 minus M rockets. So this then is going to be my height of the burnout. Okay. All right, so just on time. So that makes up for our snow day. We'll pick up from here on what is that? Wednesday, assuming we have class on Wednesday, and then we're going to start looking at center of mass type stuff, and then I'll start uh, putting up some homework since we're pretty much done with this chapter. So, yeah. So after we do center of mass things, we'll be done with this chapter, and then yeah. So I'll start putting up some homework, and let me know if you have any questions, and I will hopefully see everybody on Wednesday.